Consider the problem from the previous video. There is a message signal. But while being transmitted, there is a large background noise added to the transmission. The message, for all practical intents and purposes, is lost. Is there a better way to send signals in such a noisy environment? Yes. Consider the following analogy. A new coach goes to the field to meet his team for the first time. There are many kids. He only knows the team's name is Roaring Lions. If you are the Roaring Lions, wave your arms, he tells the kids. A group of kids do, and he knows who are on his team. Like this analogy, a way to make the signal stand out from the noise is to make it wave its arms, so that it can be recognized. A way to make the signal to wave its arms, so to speak, is demonstrated here. By multiplying the signal with the sinusoidal function, the signal is comprised with both the message that consists of on and off square pulses, which are in turn carried by a continuous, steady sinusoidal waveform. If you have learned Fourier transform, the bottom graph shows the Fourier spectrum of the modulated signal, indicating that it indeed has a frequency of 9.3 kHz, which is the chosen frequency. This method of modulation is called amplitude modulation, or AM, as in AM radio. Now, let's see the signal with carrier in the presence of noise. Although the signal plus noise still appears to vary widely in amplitude, any part with carrier high-frequency oscillation clearly stands out and recognizable. The next task is to build a circuit that can filter out the portion with carrier oscillation, the fuzzy part of the signal as seen on the scope, and rejects the rest. The type of circuit that can do this is called a filter, or more precisely, a frequency filter, or spectral filter. Before getting into the circuit, however, it is worthwhile to wrap up the concepts of carrier and modulation. Because the sinusoidal wave is used to carry the communication signals, it is called the carrier. For modern communications, from radio, to TV, to cellular 5G network, to Wi-Fi, and optical fiber communications, the sinusoidal waveform is actually an electromagnetic wave. For radio, they are popularly known as radio waves or air waves. In fact, the number associated with an AM or FM radio station, for example, AM 1050, or FM 93.3, is the frequency of the carrier used by that station. Microwaves and light are even more important to modern communications, but they are not popularly associated with communications. Electromagnetic wave carriers can fly through space, but like airplane carriers, they are not of much use if flying empty without passengers. Modern communications use the electromagnetic wave to carry information by modulation. Amplitude modulation or AM, and frequency modulation or FM, are two popular concepts. Lesser known but important with light wave communication is phase modulation or phase shift keying. Although the circuits of Lab 6 do not involve frequency modulation, it is worthwhile for conceptual demonstration next. Here is an illustration of frequency modulation. The amplitude of the carrier is constant, not modulated. Its frequency, however, is not constant, but shifted by a small amount, in proportional to the message signal amplitude. The demonstration here shows very slow rate of frequency modulation so that it is easier to see on the scope. In real applications, it is modulated at the data or signal transmission rate, which can be very high, up to a fraction of a % of the carrier frequency. Back to the question how to filter the message signal from the added noise. our eyes can recognize the signal portion as the fuzzy component. We will use a circuit that specializes in selecting the portion of signal with high-frequency carrier oscillation from that without, as shown in the graphic next. This is the high-pass filter circuit that is to be built in Lab 6. It consists of just an op-amp with 2 capacitors and resistors. In circuit theory, it is called a second-order response circuit, because its response versus frequency scales as the square of frequency. At this point, we need not be concerned with details of the circuit. It is sufficient to say that, given a complex signal, this circuit selects the portions of the signal that have high frequency oscillation, which is above 3 kHz as shown, and greatly attenuate those that are DC or oscillating at low frequency, such as low-frequency noises. The noisy transmitted signal from the left side adder circuit is input into the high-pass filter circuit on the right-hand side. The output from the filter circuit is shown next. The output of the high-pass filter circuit, top, blue, shows that the vertical random up and down of the added noise is largely gone. There remains little spikes here and there, but they are clearly distinguishable from the filtered signals, of which the key characteristics is the unmistakable high-frequency modulation over the duration of 1-bit pulse. Noise alone without noise. Only small signal alone without noise. Largely passed through. Noise alone without signal. Only small spike oscillation due to the square step edge nature of the DG-Lent AD2 simulation. It should be noted that realistic noises statistically do not have such step edges. This type of noises is among the worst case scenarios. Observe the signal being on and off alternately. One can see that thanks to the high frequency modulation, the original portion of the message signal is allowed to pass through, while the added noise, without high frequency oscillation, is not. In fact, the filtered signal, blue, top is more stable than the noisy signal, and it can be used as the triggered source. In the follow, the original AM signal, yellow, bottom, can be compared with the output from the high-pass filter circuit, blue, top. Certainly, some noise leaks through, as there is no such a thing as a perfect filter. But this must be viewed with the context of how large the noise is. Also, the filtering is not completed. There is still later filter stage that can reduce the spiky noise. Indeed, there is one more question. The signal is modulated to be carried by the high-frequency carrier. It is like someone gets on an airplane to fly through a big ocean, or a large swath of desert, or jungle. But after the flight, one must get off the carrier. In communications, this is known as demodulation, the opposite process of modulation. This is the function of the last circuit to be demonstrated in this Lab 6. Here are the next 2 steps in signal processing. The one on the right, next to the high-pass filter, is the low-pass filter. Its use, as valuable as, and is the counterpart of the high-pass filter, will be demonstrated next. The last one, to the right of the low-pass filter, is the demodulation circuit that removes the carrier's sinusoidal function, and restores the original message signal.